In supervised learning, we guide machines using label data, but in unsupervised learning, machines explore on their own. What is clustering? It is the art of grouping similar points together without using any labels or supervision. Instead of teaching machines what is right or wrong, clustering lets them discover hidden patterns inside data. Algorithms analyze similarities to form natural groups or clusters just like this. In the real world, clustering powers market segmentation, organizes online content, detect network anomalies, and even identifies communities in social networks. There is no single way to cluster data. Each algorithm has its own personality. K means it's all about centroids. It divides data into K groups by finding the most balanced centers. DBSCAN takes a density-based approach. It discovers clusters by spotting regions packed with points and ignores noisy outliers. And hierarchical clustering builds a tree of relationships, matching or splitting clusters step by step to reveal data hierarchy. K-means is the one of the simplest and most powerful clustering algorithms in machine learning. It groups data into K clusters, where each cluster is represented by its centroid or mean point. Here is how it works. Step 1. Choose how many clusters you want. That is called K. Step 2. Randomly initialize centroids. Step 3. Assign every data point to its nearest centroid. Step 4. Update those centroids and repeat until the clusters stop moving. What is the result? It is stable and well separated clusters. For example, in customer segmentation, if K equals 3, K means might discover 3 groups: budget buyers, occasional spenders, and premium customers. K means is simple and powerful. It does come with a few limitations you should know. First, you need to predefine K, the number of clusters. That is tricky when you don't already know your data structure. Second, it is sensitive to outliers. A few extreme points or poor initial centroids can completely distort your results. Third, it assumes spherical clusters of similar size and density, so it struggles with irregular shapes or uneven data. Here is a pro tip: use the elbow method. Plot the number of clusters against sum of squared errors. The point where the curve bends, the elbow, shows your optimal K value. DBSCAN, short for density-based spatial clustering of applications with noise, is a powerful algorithm that groups data by density, not by distance from a center. Instead of predefining clusters, it looks for regions packed with points, forming natural shapes, and even spotting outliers automatically. It all depends on two key settings: epsilon, which defines the neighborhood radius, and mean points, the minimum number of points needed to form a dense area. Points inside the dense area are called core points. Points close to them but not dense enough are called border points. And anything left alone, that is a noise point, called outlier. DBSCAN works by spotting areas where points are packed close together, that is density. Dots in dense regions become clusters, while scattered ones are marked as noise. It all depends on two parameters: epsilon, the radius that defines how close points must be neighbors, and mean points, the minimum number of neighbors needed to form a dense region. Points at the heart of the cluster are called core points. Those are at edges are border points, and anything too far away, that is just noise. Hierarchical clustering is like building a family tree of data. It creates a structure called a dendrogram, showing how points group together at different levels. There are two ways to do it: agglomerative and divisive. In the agglomerative or bottom-up approach, each point starts as its own cluster. Then the closest phase keep merging step by step. until everything joins into one big cluster. The divisive or top-down approach does the opposite. It starts with all points in a single cluster and split them apart recursively. Here is how bottom-up process works. Step 1. Compute all pairwise distances. Step 2. Match the two clusters that are closest. Step 3. Update distances. Step 4. Repeat until only one cluster remains. And just like that, you can cut dendrogram at any level to reveal number of clusters you want. Let us talk about linkage methods, the heart of hierarchical clustering. These methods decide how clusters are joined together based on the distance between points. Single linkage uses the closest points between clusters. Complete linkage looks at the farthest points. Average linkage takes, you guessed it, the average distance across all pairs. And the Watts method, the most popular, merges cluster that minimize total variance within groups. Here is a real world example, customer segmentation. By analyzing income and spending, we can discover high value buyers, budget seekers, and average spenders, helping businesses plan smarter marketing campaigns. What are the advantages? No need to choose K beforehand, clear hierarchies, and easy visualization with dendrograms. What are the limitations? It is computationally heavy, and once merged, clusters can't be undone. Now that we have explored all three algorithms, let us compare them side by side. K-means is simple and superfast, but it needs you to decide the number of clusters operand, and it struggles with outliers or odd shapes. It is best for large clean datasets with spherical clusters. DBSCAN, on the other hand, doesn't need you to pick K. It is great with noise, handles irregular shapes, and discovers clusters of any form, perfect for noisy or complex data. Finally, hierarchical clustering builds an entire tree of relationships, so you can decide the number of clusters later by just cutting dendrogram. It is highly interpretable but can be computationally heavy on large datasets. So here is the summary. Choose K-means for speed, DBSCAN for messy real-world data, and hierarchical when you want insight and structures in smaller datasets. Clustering is not just theory, it is powering real-world applications everywhere. In marketing, it helps businesses group customers by behavior by smarter targeting. In healthcare, it groups patients by symptoms or genetics, paving the way for personalized treatment. Finance teams use clustering to spot unusual spending and detect fraudulent transactions. In cybersecurity, it identifies anomalies in network traffic, catching potential attacks before they spread. E-commerce platforms rely on it to cluster similar products and make better recommendations. And in natural language processing, cluster organize documents and topics automatically. Let us wrap it up. Clustering helps uncover the hidden structure in unlabeled data. It is how machines discover patterns all on their own. K-means is fast and simple, but it needs you pick K and doesn't like outliers. DBSCAN handles noise and irregular shapes beautifully, though it needs careful tuning. And hierarchical clustering builds clear tree-like structures, easy to interpret, but slower on big datasets. Together, these algorithms form the backbone of unsupervised learning, empowering AI to see patterns where human might not even look.